afterwards, but I think we're just going to play a video of the talk.
Hello everyone. Welcome to the presentation of our work entitled Autonomous Intruder Detection Using a ROS-based Multi-Robot System Equipped with 2D LiDAR Sensors. My name is Masrun Islam, and I will be with you through the rest of the presentation. So I want to start off with what we had in mind for the work. We wanted to make a system that can guard an empty warehouse when humans aren't around, for an example, during nighttime. We aimed to make a system that only employed LiDAR sensors because we wanted to see how far we could go without using a camera. It had to be a multi-robot system because there are some interesting challenges associated with this. And lastly, it had to be lightweight. I'm talking about the algorithms that are intended to run on onboard systems such as the Raspberry Pi. I would like to introduce the rest of the authors. Tawhid Ahmed, Abu Tamam bin Nuruddin, Mashuda Islam, and Shahnawaz Siddiq. The first four authors are research assistants of the Department of Electrical and Computer Engineering, North-South University, and the fifth author is our honorable supervisor. A little background about our supervisor, Dr. Shahnawaz Siddiq. He's an assistant professor at the Department of Electrical and Computer Engineering, North-South University, and he has received his PhD in aerospace engineering from Georgia Institute of Technology. So these are some memories from a year back when we participated in an intra-departmental competition and secured a place. So this was when our system was taking baby steps. So the system now is much better than what it was just a year ago. And we did have the hardware to demonstrate what we were proposing. Right around February 2020, we all decided that we are going to get back to work, benchmark this system, make it better, and see where this goes. And then COVID happened. So now what do? We decided to go for simulation. And we specifically chose Gazebo because it supports sensor noise and real-world physics, which is the closest we can get to recreating a real-world scenario in our current situation. We have created map1 to test the detection algorithm itself, and this is a 6 meter by 6 meter map where we let the robots wander around while we take some data to calculate the detection performance matrix. The intruder robots and the security robots in our simulations are all turtle bots. And we have also included objects of different shapes and sizes, as you can see in the map. These objects represent intruders of different shapes and sizes. So let me introduce you to map 2, which we use for what we call the labyrinth test. And this is a 20 by 20 meter bounded region. Even though the map has a maze-like structure, the inspiration for the design came from the blueprint of an actual warehouse. We created this map to put the robots in a realistic setting and find out how increasing the number of robots enhances the security of a guarded region. So let us dive into the details of the main part of the work that we have done. I'm trying to keep this part simple as the intruder detection pipeline has been explained thoroughly in the paper. So the ROS package CostMap2D is intended for navigation purposes, but we have used it in a different way. This package publishes a two-dimensional cost map that contains values from 0 to 100. Now the robot is receiving the cost map from CostMap2D in step 1, which contains what the robot is seeing in real time through the LiDAR. We convert this real-time information into the grid map in step 2 using a threshold and a piecewise function. The value 0 in this step represents an occupied cell, and the value 255 represents a free or unknown cell. Now we make a crop based on the current position of the robot from a priority map that was saved previously. In step 4, we want to extract the common occupied cells between step 2 and step 3. This is done using an element-wise OR operation, and right after that, we subtract the real-time information in step 2 from the prior information found in step 4, and we end up with step 5. Now we have extracted the dissimilarity between the real-time information in step 2 and the prior information in step 4. The dissimilarities found are potentially the cells occupied by the intruders, and therefore we extract the contours from these grid maps and save their bounding box information. The whole process described here is done on each robot of the multi-robot system. Now, if you have noticed, most of the operations in the steps shown are simple element-wise operations. That means we have the option to use optimized implementations of such operations. Also, element-wise operations can be run in parallel. This means we can take advantage of multi-core CPUs and GPUs to increase computational throughput. So here are some real examples of the steps that I've talked about. Step 2 being the real-time information that is seen through the LiDAR. Step 3 being the cropped out section from the global map. Step 4 having the common occupied cells between step 2 and 3. Step 5 having the dissimilarities extracted by subtraction. And lastly, step 6 having the bounding boxes drawn around the dissimilarities that the robot found. We have another robot that does not necessarily have a physical appearance. We call it MIDNET, that stands for Multiple Intruder Detection Network. It processes information from all the robots that are connected to it. And by information, I mean the bounding boxes that each robot stores. Finally, MIDNET produces a fused list of detections that is free from duplicate detections and also the detections produced when the robots see each other. MIDNET fuses the duplicate detections using a divide and conquer approach, which makes the process computationally efficient and theoretically enables MIDNET to use information from an infinite number of robots. The bounding box information received from each robot consists of only 2 sets of X and Y coordinates per detection, and the small data footprint means that MIDNET can normally receive information from robots even over weak wireless networks. Lastly, MIDNET uses intersection of a union when it needs to decide whether 2 detections correspond to the same entity. So now let's move on to the deduction test. This is the single robot case. The clip has been sped up since everything was running in slow motion. Next comes the deduction test for the 5 robot case, or what we call as the multi-robot case. And this clip has also been sped up. About 2,000 frames have been observed for each case, and the 1 robot case took about 23 minutes, which is 5 minutes in simulation, and the 5 robot case took about 1.5 hours, which is equivalent to 8 minutes in simulation. The 5 robot configuration performed better than the 1 robot configuration in our test, as shown by the F1 scores. According to what we have observed, this happened because the 5 robots covered a lot of blind spots that was created, particularly when a smaller intruder hid behind a bigger intruder, which helped in the reduction of false negatives in the 5 robot case. The spike in the false positives seen in the 5 robot case was mainly due to the fact that a very big intruder was appearing as 2 intruders to the robots. So, for an example, if a big intruder is separating 2 security robots, the robot on one side will detect this as an intruder, and the robot on the other side will also detect this as another intruder. This is harmless as this only makes the system provide an overestimate of the number of intruders that it is seeing right now. Next comes the bigger map that I have shown earlier, and the sole purpose of this test was to actually analyze whether increasing the number of security robots enhances the security of a guarded region, specifically the guarded region that we are going to show now. This is a one security robot versus 3 intruders, and the footage has been sped up. I've used a 7-year-old gaming PC for all these simulations, and I'm glad that it could take all that torture. The last footage is of 5 intruders versus 5 security robots, and this is just one of the trials that we have conducted for each combination. We have conducted 20 trials for combinations of security robots and intruders, and therefore we had 25 combinations in total, because we went from 1 intruder and 1 ranger all the way up to 5 intruders and 5 rangers. And that means we had 500 trials in total. The simulations took in total about 4 days, that is, to be exact, 92 hours. And this is equivalent to 17 hours of simulated time. We have calculated success rates for all 20 trials for each combination using the formula given. We have then calculated the average success rates for each combination and plotted them in the graph shown. For this test, we have done random assigning of patrol coordinates to the robots and also spawned intruders at random locations and assigned them random escape locations. This ensures that the tests are fair, and the trends that we can see in the graphs are therefore due to increasing the number of security robots. Finally, the graphs do confirm that increasing the team size enhances the security of the guarded region. So where do we want to take this research now? We want to test everything in a complex environment. And by a complex environment, I mean, for instance, a house with a lot of furniture. We also want to find out how we can use 3D LiDAR in our system. I want to thank you all, and it is an honor to be able to present our first work in robotics in SSRR 2020.
Maybe I can take some questions. Yes, yeah, very welcome. Yes, one of the things that come to me is this system that you use as a middle layer. This looks like an architecture by Z on the previous architecture from control and also distributed control where you have a blackboard. So do you have any reason why to use this centralized scheme?
You can hear me, right?
Yes, I can.
Okay,
we can.
Yes. So basically, it was more efficient for us to actually join all the robots' information using the divide and conquer approach. So specifically, we have followed the divide and conquer approach. So a little example would be the merge sort problem, like how the merge sort problem is solved. So this specific architecture of MidNet, the central bot I'm talking about, we followed that because even if one robot is connected out of, like, if it's somehow excluded out of the system, even if there is a central point of failure, that robot will not cause the whole system to fail. It can instantly work with the other robots. Like, for an example, there are 10 robots and one robot just failed. It will know that one robot is not there, but it will not fail itself. It can join information from all the other robots, and we don't have to take extra measures for it. This is originally from the algorithm itself.
Yes, it's like a closed centralized system. Yes. Okay, thank you very much. Yeah, and ROS also allows to do that. That's
yes, of course.
Thank you.
Can I ask, did you do any comparison of different sensing modalities? For example, comparing LiDAR with cameras, radar, infrared?
We really wanted to do that, but the short time frame did not allow us to do so, actually. Since we had to put a lot of effort in setting up the whole experiment. Since everything was in simulation, from my experience, I would say setting everything up in the real world is easier than setting everything up in simulation, because like there are a lot of things that are really hard to put in a simulation. One advantage that I found is we can have that ground truth. So that is one advantage that we found during, when we made our the whole world that we just showed. So we want to experiment or compare with cameras and other sensing technology and see where how we can actually make this viable, and most probably, or like hopefully in the near future, this might be something that everybody uses.
Are you moving now from simulation towards real world testing?
Well, right after our restrictions are off, when we are allowed to go back to university, we will start doing this.
So that's the next step.
That's the next step, of course. Because even I myself, I am a big supporter of real world experiments, but we did not have an option to do anything. Even we cannot really, our workstations are in the university, so I had to depend on my own computer for this.
Right.
Yeah.
Thank you, Mashlin. Any further questions? If that's it for questions, then that's the end of this session. Next up, we have an invited talk at 11 o'clock from Professor